welcome to the second lecture on hardware security. So, as in the last class we were introducing ourselves to the topic of hardware security. So, I will continue with that and try to see some more implications on hardware security in the present day context. So, I will start with the elaborations on the concepts that we will be covering in today's lecture. So, we will be trying to see about root of trust, which is one of the fundamental objectives of hardware security. Like we try to develop a root of trust using the technology of hardware, and in this context we will be discussing about something which is called as trusted platform modules or TPMs. So, we will be also discussing about hardware attacks in this context, like some of the attacks which were mounted on TPMs and essentially have challenged the opportunities which hardware in general brings in. We will be also touching upon side channel analysis and also talk about in general about trust in hardware, and finally, we will be discussing about a hardware design flow, like trying to understand how we can eventually design hardware using our basic CAD tools. So, to start with, let us take a look at developing a root of trust, which is a very fundamental I would say fundamental objective of bringing in hardware is that we try to we develop a like a very minimal component which is called as the root of trust or ROT. So, in this context there is a very important objective, like you would like, for example, suppose imagine that you have a computing system and you would like to boot your computing system. How do you know that the operating system that you are loading, right, essentially is trusted? Because many of the attacks we know essentially which happens on software happens because of the fact is that the operating system is itself compromised. So, even if you like run your software which essentially has, for example, cryptography in it, right, will not be enough, because the OS on which the software is executing is itself compromised. So, in order to address this, there is a concept of secure boot which I will try to introduce here. So, in trusted boot there is a basic component which is essentially hardware. So, the basic root of trust is hardware, and it tries to initiate a chain of trust. Okay. So, the idea is that there is a small component which is essentially your system hardware as shown here. It tries to essentially basically what it tries to bring in is it tries to develop or basically like this is the starting point of your root of trust. Okay. So, it tries to measure or bring in the initial BIOS code, but before it executes the BIOS code it does a measurement. Okay. So, this measurement is trying to understand that whether the BIOS is legitimate or not. Okay. So, what essentially is measurement can be discussed, but let us try to get the overall idea. Okay. So, what we try to do here is, or the root of trust or the hardware root of trust tries to do is, it tries to initially measure the initial BIOS code, and then so the measurement could typically imply very simply take the program, take its configuration and compute a cryptographic hash on it. Okay. So, therefore, what it tries to do is it tries to develop this measurement or calculate this hash output, and let us call it as measurement of the BIOS. Okay. And once the measurement is done, it is appended to a chain of trust. Okay. So, we append this, and if this measurement does not belong to an approved list, this approved list is denoted as L star, then the process itself halts at that point. Okay. So, the process itself stops at that point, and it does not allow it to go further. On the other hand, if the measurement is fine, that means if the measured output belongs to an approved list, then we continue. So, then we go into the next layer where we basically, so now the BIOS comes into the picture, the BIOS takes control, and the BIOS starts to measure and execute a bootloader. Okay. Again the same process continues, that means this measurement is done, the measurement is appended. If the appendment is fine, if the appending is fine, then it is allowed, otherwise it halts. Okay. So, finally, the operating system comes into the control, and the idea is now therefore that if you go behind, right, if you consider this chain of trust, then the entire trust is built upon this assumption that the hardware which is your root of trust is pure, is essentially trusted. Okay. So that is that is essentially the reason why like hardware is very promising, because it can give you a very small component which you can trust, okay, which you can believe, and if this works fine, right, then virtually you have a very low cost and efficient way of building trust to your systems. Okay. So here is a reference which you can look into. It gives a very nice description about several other things related to secured boot and also TPMs in general. Okay. So therefore, this essentially brings into this concept of trusted platform module, or TPM. So TPM is basically a technology which essentially, right, is tries to bring in trust into your system, and it's a standard. It's a standard of trying to build in trust in your system using this concept of minimalistic root of trust, okay, which is built in hardware. So the idea is that a trust there are many definitions of TPM. Like here I have enlisted one of the popular definitions, which says that a trusted platform module is a computing platform that has like a trusted component, probably in the form of built-in hardware, just like what we saw in the previous slide, which it uses to create a foundation of trust for your software processes. Okay. So there are different components of a TPM chip. For example, here is sort of a diagram which tries to capture how a TPM chip looks like. So I will just try to show you the most important components. So one of them is, of course, there is a LPC bus. So it's a low pin count bus, and which essentially does the input output. So it does the I/O with the external world. Then there is a secure controller. So this controller controls the internal TPM execution flow and verifies the command. Like suppose you give a command to the TPM chip, the commands are often encrypted and they need to be verified to know that they are legitimate commands. Okay. So then there is an EEPROM which basically stores several keys. So in TPM there is a management of several keys, okay, and I have just enlisted two of the most important ones. So one is called as an endorsement key, and the other one is called as a storage key, or SRK. Okay. And there are also other important keys like owner authorization data and EK certificate, which are also maintained and stored inside the TPM. Okay. So you may note here that the EK and the SK, or the EK and the SRK, never actually leaves the IC boundary. So this essentially remains embedded, and in particular the private component of this. So these are typically based on public key cryptography. So they have a public key and a private key component. The private key components of these keys, like of the endorsement key and so on, the SRK, never leaves the IC boundary. So it basically remains inside the TPM chip and is never externally exposed. Okay. So this is a feature of the TPM chip. Okay, and there are some criticism against that also, because of the fact that even the user who is using the TPM chip is not aware of these keys. Okay, so this can lead to some privacy allegations and things like that. But at least from security point of view, this seems to be a very like a sane solution, where the idea is that the chip essentially is kind of storing the secret key, and this secret key component is never externally revealed. Okay, so even the user of the TPM chip is not aware of these keys. Okay. So that is essentially the basis of this like of the trust which is built using TPMs. And the TPM, right, as you understand, does lot of cryptographic operations, and because of this there are some cryptographic components which are already being inbuilt into the TPM chip. Okay. So for example, it has got a support of a 1024 bit or 2048 bit RSA key generation as well as RSA encryption. So it can do both key generation as well as encryption. Okay. Then there is a SHA-1 engine. So this is a hash engine. Okay. So there is a hash function, as I said, that when you are doing the measurements, you are doing hash computations, right. So therefore, what you are typically doing is that, so there is a platform configuration register, okay, and this stores the stores the current calculations, like the current measurements. Okay. So the measurements are usually done in this way, like you take an initial PCR and then you do an hash of a new code. So you kind of do something like an iterative hash function. So you apply the hash function one after the other, and you try to compute this digest, and you try to keep it inside your PCR. So then one of the fundamental requirements of cryptography is that it requires or is based on random number generators. Okay. So therefore, the TPM also has got a small hardware or a hardware for doing or calculating what are called as TRNGs, or true random number generations. So there is a true random number generator which is inbuilt into this. Then there is a tick counter, which is essentially provides an audit trail of all the TPM commands which are arriving at the TPM. And the idea is that this is a very, like a built-in with lot of security features, so that you cannot do like active attacks. So it has got an active shield, it has got voltage fluctuation detections and high frequency sensors, reset filters, and so on. So these are basically, I would say, more of like safety measurements which are being kept in the TPM chips. Okay. So, like having said that, TPM is also upgrading. So the one which I told before was more of like TPM, what is called as TPM 1.2, which is getting upgraded into TPM 2.20, and note that TPM 2.0 is not backward compatible, but TPM 2.0 comes up with many other algorithms. Okay, for example, it has got support of not only RSA, but it has also got support of elliptic curve crypto systems, which supports like NIST P256, Baratone curves. These are different forms of curves which we need not, which we will probably see at least some of them in our future classes. But as I mentioned you in the previous class also, like elliptic curve crypto is a very popular and efficient way of developing public key cryptography, and TPM 2.0 apparently also supports the ECC. Then the SHA-1 is of course there, and also it has got extended to SHA-256, which is an improved hash function, okay, or a modern hash function. Then there is a support of a 128-bit AES encryption, and along with this there are several other algorithms which are also defined in the specifications of TPM 2.0. So here is a reference if you are interested from Wikipedia about how TPM 1.2 compares with TPM 2.0. But having said that, I mean, the point which I want to kind of hit upon here is that in spite of this, there have been reports of several hardware attacks on TPMs. Okay, so I have just enlisted two of the very important attacks. One of them was told in 2010, where researchers at Black Hat showed how to extract secrets from a single TPM by inserting a probe and spying on the internal bus of an Infineon chip, okay, which has got TPM. So basically they probed the bus and found out the secrets. Okay, and as I said that if those secrets like EK and so on and SRK are revealed, then the entire trust collapses. Okay. Likewise, in 2015, there was an attack on a power attack. So this is a side channel attack, okay, and we will be studying what differential power attack is and how it works. So the idea is that a DPA essentially was mounted to extract the secret keys. Okay, so this shows that even if you have a nice architecture like TPM, the idea of storing secrets is not a very I would say safe and secure means, okay, because there can be potential attacks. At the same time, it also tells us that we should build our crypto systems or crypto hardware with these kind of physical attacks in mind, like with this kind of side channel attacks in perspective. So this brings us to the topic on hardware attacks. So basically what I'm trying to say is that although hardware comes up with lot of advantages, and it basically rules out several attacks on the software, but then there are some challenges on its own which are essentially challenges because of its nature of being hardware. Okay, so for example, when you talk about hardware, you can actually monitor several analog signals. For example, you can monitor the time taken, of course, like it is there even in software implementations. But if there are time variations, for example, if you have say a sequential circuit which you have implemented and the output comes up depending upon the input. Okay, so then you can immediately do few attacks. Okay. Likewise, the power consumptions, electromagnetics, sound, etc., all of them can be potentially used to attack. Okay. So for example, you can probably appreciate this point that when you try to do traditional hardware design, you try to minimize power. Okay. But when you are trying to develop secure hardware, your objective maybe maybe not that, maybe rather than of course you have to minimize power, but what is more important is that you have to make or ensure that the power consumption doesn't vary with your inputs. Okay, because if it varies, then the attacker can catch those variations and from there can try to obtain the secrets. Okay. Likewise, you can do physical attacks like fault attacks, for example, where you can perturb the environment, you can perturb the voltage you can create temperature fluctuations, you can take UV light, you can use X-rays, lasers and so on to create bit flips in your circuit. Okay, and we will see later on in our discussions how you can use faults effectively to get the secret keys with very less effort. Okay. Likewise, you can also do invasive attacks, you can probe data and you can modify circuit. So in this context, there is a technology which is called as focused ion beam or FIB, which can actually create test points and even modify the chip structure, okay, from the rear side of the chip, and thus it can overcome sophisticated top metal mesh protections and sensors. Like you may have in the top layer, like you may have mesh protections, you may have protections against attacks, but the attack essentially takes place from the rear side, from the rear structure. And these are like extremely sensitive and powerful equipments which are expensive, no doubt, but they are definitely feasible, okay. And therefore, right, we need to take care of these kind of hardware attacks when we are designing our secure systems. So, hardware security bridges the gap between theory and practice. For sure, as I said that like cryptographic theory has limitations, because cryptographic theory often doesn't address the real world, okay, and there is an absence of theory for the reality, because of which even mathematically strong ciphers can leak in the real world. So, you may take a nice AES algorithm or an RSA algorithm or an ECC algorithm, but when you implement them, right, because of this leaked information through what are called as side channels, which may be intentional or it may be unintentional, the secrets can be compromised, okay. So, therefore, what we need to do is that we need to understand this gap between theory and practice, okay. So, therefore, right, there are several goals which we will be trying to address in our course in due time. Is that we of course need to take care of performance, which is like one of the most important reasons why we have hardware, because we want to make our designs more efficient. So, we want to of course take care of speed, clock frequency, latency, do fast arithmetic, okay, bring in parallelism in our computations, okay. But at the same time, of course, like we have to also take care of some other things, okay. The another very important thing which is of importance in more probably in today's world when we talk about Internet of Things and cyber physical systems is that we need to make our designs lightweight. So, we need to make our designs consume less area, take low power, take low energy and so on. But even with this kind of constraints, right, we cannot compromise on security, because if security is compromised, then the entire technology will collapse, okay. So, we need to take care of side channel attacks, fault attacks, and also countermeasures. Like when we build in countermeasures, as we will be seeing in the class, they are extremely they have a high overhead, okay. So, we need to try to ensure that the countermeasures are light and they can be utilized for IoT kind of subsystems. So, I will in the remaining part in today's class, I will be trying to tell you about how we can actually develop hardware, okay. So, of course, there are different ways of designing hardware, like there are application specific integrated circuits, ASICs, which may be costly, okay. There is another competing technology which is called as the FPGA, which we will be trying to kind of like focus in our class, okay. For example, an FPGA stands for what is called as a field programmable gate array. So, it is a very interesting technology which is basically comprised of an array of logic cells which are connected by routing channels, okay. So, the idea is that if you go into the name of FPGA, you will see that there are certain important parts, okay. One of the interesting part is this programmability, okay. So, it says that it is programmable. So, it is a hardware which is programmable. We know that our general purpose computers, when we have general purpose computers, when we write programs on them, then it is programmable, right. So, you can write any program, you can write today bubble sort, tomorrow quick sort on the same architecture, okay. Likewise, when you talk about FPGAs, you can actually reconfigure it. So, you can reconfigure an adder and to maybe work tomorrow as a multiplier, okay. That is the biggest advantage of an FPGA. So, you can actually do an in-house design, you can do a design inside your house, inside your lab environment, and you can go from your basic conception of the design to the final execution, okay, in situ in your lab. And like because of this, the technology is interesting, because the technology you will see has got an array of logic cells which are connected via routing channels. There are special IO cells, and the logic cells are typically what are called as LUTs. So, these LUTs are essentially like the fundamental blocks of FPGA. So, let us take a look about how an FPGA like looks like. So, here before that here I have kind of enlisted some applications of FPGAs. For example, I think that one of the biggest advantages of FPGA is to prototype. Like before you are going into commercial deployment of an ASIC, as I said that ASIC is costly, you would like to prototype your design. You would like to see that whether your design at all works fine or not. And there is a huge application of FPGAs, okay. And the production cost is less, because there is a very less time to market. You can get better performance, and the modern FPGAs are improving in leaps and bounds. So, the bridge or the gap between ASICs and FPGAs is also like getting lesser and lesser. So, our FPGAs nowadays are pretty advanced. So, you can really develop, I would say, competing technologies on FPGAs as well, okay. because of various dedicated blocks that they have, like DSP blocks, multipliers, and so on. Another thing, as I already said, is that it's reconfigurable. So you can also do, like you can make the same hardware to reconfigure, and also you can reconfigure on the fly. So with techniques like partial reconfiguration, you can actually do dynamic reconfiguration, okay, and that is a huge advantage which FPGAs brings in, okay, particularly in the context of things like IoT and those kind of things, where you probably need to change things very rapidly. Then also you can develop special purpose computing platform. So for example, dedicated to solve one problem, and this is exactly where you can bring in crypto, because in crypto, right, you need to solve dedicated problems, and therefore in this context you can try to bring in or develop FPGA accelerators, okay. So let us take a look about, okay, so before that, here is a classic example of a DES cracker. So this design is called as Copacabana. So many of you probably know about the DES, or the data encryption standard. So in 1998, a custom hardware was developed to develop an attack on this, and you can see the cost. It was something like $250,000 to build and decrypt DES cipher in 56 hours. Later on in 2006, there was an effort which was called as Copacabana, which stands for Cost Optimized Parallel Code Breaker, which was built, and it was built on commercially available reconfigurable integrated circuits, and the cost reduced to something like $10,000 and decreased DES cipher in around 6.4 days. Okay. So the cost decreases by roughly a factor of 25. Okay. So if you just adjust for inflation over 8 years, so you can see that even you can see the improvement is probably in around 30x. Okay. Now since 2007, there have been several efforts. So for example, this is an example of a spin-off company which tries to develop successors of Copacabana, and one of the successors of Copacabana is called as Rivera, okay, and it reduces the time to break DES to the current record of less than 1 day using 128 Spartan 3 FPGAs. Okay. So this is an interesting example, and this is a Wikipedia link where you can go and see how FPGAs can be used to develop custom attack hardwares. Okay. So that, so here is a photograph of how the Copacabana looks like, okay, and you can see it's like made up of nice structures we are built around FPGAs. So here is a diagram about how an FPGA architecture looks like. So this architecture is what is called as the island architecture. So in this architecture, you will see that there are some IO blocks. So these input output blocks are located around the periphery of the core of the chip, and the objective of an IO block is just to develop connectivity of the chip. That means the chip tries to communicate with the external world through these IO blocks. Okay. The other important block is the logic block. So this logic block is where your logic resides. Okay. So this logic block is comprised of what are called as CLBs, or configurable logic blocks, which are in turn made up of what are called as LUTs, or lookup tables. Okay. So in general, this architecture may vary from slide to slide, from vendor to vendor, but more or less this is how it looks like. Okay. So you have got the logic blocks, and these logic blocks essentially are interconnected with, they are interconnected with each other. They are interconnected with the power, with the lines around, and for that you also have got special blocks. So these blocks are what are called as the switch blocks and the connection blocks. So if you see this diagram, you will see that there are two important routing points, okay, and they are all switches. Okay. So for example, this logic block is connected to these rails, okay, and these are essentially what are called as the connection blocks. For example, if you see this logic block, it is connected with these rails, or the wire segments around the CLBs. They are connected by programmable switches. Okay. So you have got programmable switches which you can configure to get connected. Okay. Likewise, right, if you take the wires in adjacent channels like this channel and this channel, they are connected here by what are called as switch blocks. Okay. So these are nothing but interconnection logic or interconnection switches which you can program. So for example, if I want to turn on a switch, I need to say, like program 1 over there. Whether, if I want to turn off that switch, I will program it by 0. So it's basically using switches or maybe digital switches, to be more precise. Okay. So at the end of the day, what you are trying to do is that you have a design, and your tool, right, will give you a 0-1 pattern, which is often called as the bit file, and you take that bit file, and the bit file configures these switches. Okay. And therefore, right, the FPGA gets reconfigured, and not only the switches but also your lookup table, okay, and your entire structure gets reconfigured to work as you wish, okay, or as you intend. So here is how the internal of the CLB. So this is slightly on an older FPGA. So but I think the idea remains the same. So you will see that in the CLB there is a block which is called as the LUT or the lookup table. Okay. So this lookup table typically always have a fixed number of inputs. So the number of inputs here are designated as 4. Okay. In modern FPGAs you may probably see it go up to 6. Okay. So there was an older work where people tried to do lot of explorations trying to find out that what should be the size of this input of the LUT, okay, whether it should be 4, 5, 6, 8 or so on. So it was found out that if the value is around 4 or 6, right, around this point, it was found out that the utilization of the lookup tables is maximum. Okay, and therefore, right, you will see that if you when you are realizing Boolean functions, then most of the FPGAs typically have got inputs which are within 4 to 6. Okay. So therefore, I mean, we have the LUT block. So this LUT block can realize any Boolean function of 4 input in this diagram. Okay, if it is 6, then it can realize any Boolean function of 6 input. Sometimes in modern LUTs you don't have only one output, but you have got 2 outputs also. Okay. So but anyway, without loss of generality and without losing too much information, we can think about this architecture right now, where we have one output in the LUT and there are 4 inputs to this LUT. Apart from this, there is also a control and carry logic, which is a combinational block, which is often a fast carry chain. Okay. And this fast carry chain essentially is used to pass on your input carry to the output. Okay. So now what you can do is you can pass this input carry and calculate the output, and from there you will get a fast carry chain. So for example, right, if you are trying to implement an adder, for example, you know that the biggest hurdle of implementing an adder is a carry chain. So you can actually implement an adder nicely in this structure, where the lookup table does your other computations, but the carry chain is a dedicated path, okay, which is much faster than your other LUT blocks. You also have like a flip-flop, which is essentially supposed to provide you support for the sequential logics. So you can see that you have got support for combinational logics and sequential logics. In together you can actually realize, or this basically functions as your basic logic block. Okay. So this is how the design flow looks like. So the design flow you will see has got, or it starts with what is called as an RTL description. So you start with an RTL description, you have got a design and you start with a basic RTL. So you can implement your RTL using say Verilog or VHDL or some other languages, but typically Verilog is a very standard language which is adopted. Then you pass that to several CAD tools. Again, you have got several CAD tools, like you have got Xilinx and so these are like, I have just written more here about the FPGA tools which are used, but if you go into the ASIC world, then there are other tools like which are designed by Cadence and Synopsys. So if the idea is that you basically do an implementation here. So the implementation will include blocks like placement and routing, and finally the bit stream generation. And once the bit stream generation is done, you essentially can download that bit stream through a port which is often the JTAG port, and you can configure the FPGA to work as you wish. Okay, so you basically can reconfigure the FPGA. So this is how the overall design flow looks like, and what I will try to show you was one of the sample boards which you can probably try to get access to, is a relatively low cost FPGA device which is called as a Nexus 3 board, and we can actually, so this is the FPGA inside the board, and what we will be trying to do is we will be trying to program this FPGA using our design and typically and reconfigure it to work as we want. So I will take a simple design problem and try to show or illustrate about how and how basically we can do design on these FPGAs. Okay. So to start with, you can take a 2-bit adder. So your objective is to build this logic of S equal to A plus B. So when you want to do that, your starting thing is writing or developing a design file. So this design file is often described in Verilog. Okay. So I am not going into the syntax of Verilog, because that maybe you can look into yourself. So there is a module description. Inside that you develop the logic for the adder. Okay. Once you have developed that adder, you take it through a flow. So here is a Xilinx design flow. Here you can choose the target FPGA, write the corresponding family, device package and other stuff, and then you can actually pass it through some sequence of steps. Okay. And finally you will get the bit file. Okay. So the bit file, so here is your adder logic. You also want to test your design. So you want to know that whether your design is correct or not. So the usual way of doing that is by writing what is called as a test bench. So, you write a corresponding test bench of your adder. So, if you see the test bench, right, I mean again without going into the syntax, you basically instantiate the adder, which means you kind of can send inputs to the adder, and the input sequence is denoted here. So, you are basically giving stimuli to your adder. So, you are giving say a 0 0 as an input, or a 1 1 or 1 3 as input, and so on. Now, this adder will essentially give you the corresponding output, and you can actually verify whether your adder is correct or not. So, usually what you do initially is you do a simulation. So, you basically do a simulation which is called as a behavioral simulation, and gradually as you go down the design cycle, you do more and more accurate simulations. Okay. So, there is another, when you are trying to really port this design onto the FPGA, you also have to do what is called as a user constant file, or UCF, where you have to describe how the interconnection between the FPGA and your Verilog code. For example, the Verilog that I wrote has inputs like A0, A1, B0, B1, S0, S1 and S2. So, these are the outputs of the adder. You can actually tie it to the FPGA pins by these LOC configurations. Okay. So, for more descriptions, you can actually look into the Nexus 3 board manual. From there you can actually get these descriptions, and accordingly you can write the corresponding UCF file. Once you have done that, you can go into the implement and press synthesis step, and automatically your tool will go through a bunch of steps. Okay. And these steps essentially have got several important components. The first important component is that it does an RTL design, so like you already done this RTL design. Once you have done these like the next step which is done is what is called as an RTL elaboration. So, in RTL elaboration, what is done is that it basically infers your design into data path components, okay, or control path components. The data path components are essentially realized by special components which are internal to the FPGA, and the control path gets elaborated into either an FSM or some Boolean logic. Okay. So, there are several optimizations which are done. Some of the optimizations are architecture independent, that means they are done by usual compiler optimization techniques like constant propagation, strength reduction, expression optimizations, whereas the control paths are optimized by FSM encoding and state minimization. So, and on the other hand, the next steps which are done are more specific to the FPGA, where you actually do a mapping. So, the mapping is where you basically take various elements of the design and you optimally assign to FPGA resources. So, the FPGA resources essentially like typically like the data path elements gets inferred to adders, multipliers and memory elements, and the control paths are realized in the FPGA blocks and in the FPGA logic block often. Okay. So, the optimizations are often depend on the FPGA fabric, like the LUT structure, like whether it is for 4 input LUT and so on. Then it is followed by two important steps which are called as placement and routing, and finally you get the bit stream. Okay. So, once you have got the bit stream, that is the final step, because the bit stream takes the routed design as input and produces a bit stream which programs the logic and interconnects. Okay. As I said that all of them are programmable. So, you can program, and everything is a switch, and therefore, in this you can actually program them, either turn on or turn off the switches. So, finally, you open the tool from Adept. So, there is just an example, but you can do it with other tools as well. So, then like you basically download this bit file, and finally your design works as intended. Okay. So, reference, you can actually take a look at this book. You will find more details about how like the design works and how these designs can be made. And this is a standard reference which we will be trying to follow in most parts of the class, although we will try to use some other materials as well. So, what we have discussed in today's class is we have discussed about TPM, which is a hardware security core processor to work as a root of trust. Okay. And the hardware attacks, and we just say that even when we are using hardware, then still attacks are possible in the form of specialized hardware attacks. We are often called as side channel attacks. FPGAs provide a reconfigurable platform for hardware design. So, it is very handy not only to understand designs, but also to really develop applications using for hardware. And the FPGA design flow typically takes the RTL description, which is often done using languages like Verilog, which are high level description or hardware description languages, which are high level languages. And finally, you take it to the prototype, and the prototype is usually done in the form of bit file. So, you create a bit file and then you download that into your design, and your design starts working. Okay. So, with this I would like to conclude this part of the class, and thank you for your attention, and we will take the next class where we will be trying to look more into hardware designs.